All right, continuing on with waves. Someone around the corner from you, what is the main reason you can hear him speaking, but you cannot see him? So we've discussed this in class. We observe the wave nature of things when the wavelength of whatever wave it is that you're talking about is comparable to the size of the obstacle. So light waves, we measure those in nanometers. They're very teeny tiny things. We tend to we only observe wave nature of light when it's traveling around tiny little obstacles, which is why so much of this chapter is dealing with slit interference patterns with really narrow slits. Sound waves, on the other hand, can have much longer wavelengths, meters to tens of meters. So it's basically is that sound waves have long wavelengths, so they can bend. So we notice their diffraction much more than we notice the diffraction of light waves for the type of obstacles that we tend to have in our rooms. Sound reflects off of walls. Light reflects off of walls too. That's not true. Both of those would reflect off of walls. Sound travels farther than air than light. That's not true. Sound can travel through walls, but light cannot. Sound doesn't travel through walls well, I shouldn't say that. Yeah, that is not true either. Okay. As a light wave travels as a plane wave from air into water, which diagram shows the correct wave fronts. So inherent to being able to solve this question is the realization that the only thing that is not changing here is the frequency of the wave. So as one wave passes from one medium to another, it doesn't matter if it's an electromagnetic wave, a sound wave, a wave on a string, a wave in a tube, any wave, the frequency does not change. So if we are looking, or we're going to look at light, all right, C is wavelength times frequency. That there is not changing. The frequency is not changing. And we are trying to figure out what happens to the wavelength of the waves. So kind of drawn diagrammatically here is some wave fronts. So that distance there is the wavelength of the wave. So you might think about this as being a wave that goes like that. Where the crest, we're sort of marking the location of the crest of the wave at each spot. So we have the wavelength getting longer, the wavelength not changing, or the wavelength getting shorter as it travels from air into water. So the wavelength is going to be C over F. And I know that the speed of light in air is going to be faster than the speed of light in water. So this is bigger for air, which means that that is going to be bigger. So we have a bigger wavelength in air, and so there's only one that matches up with that, and that is this one. So we have a big wavelength followed by a small wavelength. Next is we have two beams of light. Start out at the same point in phase, and they travel different paths to arrive at a point. Maximum constructive interference will occur for wavelengths that travel by a whole number of wavelengths. So you always have constructive interference when the number of wavelengths that they travel is the same, whole numbers of integer wavelengths. And if you are traveling half wavelength differences, then you'll have destructive interference. So the way that this looks is that if you have a wave that looks like that, draw two wavelengths of it, and then you imagine having another wave that picks itself up and travels a single wavelength more. That second wave is going to look like that. So where they're matching up in that spot, we have peaks and troughs matching. This will be a constructive interference. So if this dotted wave, for every sort of single wavelength difference distance that it travels, will have constructive interference. If we were looking for destructive interference, I'll draw what that would look like. So here's the same initial wave. If we pick this up and we only move it a half a wavelength, then we would have something that looked like that. This is two waves that are canceling each other out. So we have crest meeting trough in every spot. So if you add those together, then you'll get destructive interference. So any sort of half wavelength shift will be destructive interference. Any whole wavelength shift would be constructive interference. And that is a particularly relevant question to prep for the last question on the review sheet, which is one of few very totally new questions. I think you haven't seen this semester, which is that I have two microscope slides, and the slides are exactly parallel to each other. And the top slide is going to slowly move upward. So what's going to happen as this top slide moves up, but the bottom slide moves down, is it's this distance, which we tend to call T, is going to get bigger and bigger. I'll draw this a little bit zoomed in. When we've done this in class, we've imagined that there's this incident ray. Some of it is immediately reflected, and some of it is transmitted through the gap where it gets reflected through there. And what we would like is to have this extra distance here, which ends up being about twice the thickness of the gap. If it is kind of equal to an integer number of wavelengths, then we'll see constructive interference, and we'll see something that is bright, or I guess white in the wording of this. If it's a half wavelength difference, then you'll see destructive interference, which would be all black. So what's going to happen as this separation gets bigger and bigger and bigger is that we're basically going to oscillate back and forth between distances here where 2t is a lambda, an integer number of wavelengths, and as it gets bigger, we'll get to twice the thickness is 3 lambda over 2. Twice the thickness is 4 lambda over 2, or 2 lambda. So as we increase this distance, that thickness is going to keep getting bigger and keep kind of changing how much extra distance the transmitted ray travels. So what we will see is some black, and then some white, and then some black, and then some white as this raises up. So that's the answer to that.